Space, a vast frontier still largely unexplored, beckons us with new challenges and opportunities for discovery. In this program, we'll take a closer look at the stars that populate our vast universe. We'll find out about how stars are born, their life cycles, and how they die. And we'll learn more about our own star, the Sun. On a clear night, some 5,000 stars are visible with the naked eye. But with the aid of a telescope, billions upon billions more can be seen. About half of these are actually double or binary stars, or multiple star combinations. Located at the very heart of the Orion Nebula, the trapezium is the most famous multiple star system. It's one of the youngest star clusters known. The four brightest stars can be seen with the unaided eye as the middle star in the Sword of Orion. Many of what appear with the naked eye to be single stars become galaxies when viewed through a telescope. Each galaxy is composed of millions to hundreds of billions of stars. Our own spiral galaxy, the Milky Way, contains more than 200 billion stars. And there are galaxies upon galaxies as far back as we can see, almost 14 billion light years back in the past, to the Big Bang that created our universe.
If you want to look out, of course, light has to be coming back at you for you to see it. And it's only had 13.7 billion years at most to travel. So it means you can't really see further than 13.7 billion light years. The stuff that's out there beyond that, even if the light headed towards you right when the universe began, it still couldn't have gotten here, so you couldn't see it. So that does put a limit on how far we can see.
The Hubble Space Telescope took a picture of the universe that shows 1,500 galaxies in a tiny patch of sky no bigger than a grain of sand held at arm's length. Protostars, main sequence, red giants, white dwarfs, neutron stars, black holes, each represents a stage in the life of a star, but not all stars will go through all these phases. All stars begin their lives in a large interstellar cloud of gas and dust called a nebula. The nature of gas is to expand, but if the cloud contains sufficient matter, the force of gravity will cause it to contract. As the nebula contracts, it heats up and fragments into smaller pieces called protostars. The pressure and temperature at the core of each protostar increase until a nuclear reaction is triggered, and a main sequence star is born.
The main sequence phase is the phase where the star is pretty stable. It's having hydrogen fusion going on in its core. That's where its energy is coming from. That's what makes it shine. And there's a nice balance between the amount of energy that's flowing out of the star and gravity is trying to push the star in, and they come into balance and they stay in balance for this very long time. So that's called the main sequence.
Nuclear fusion reactions in the core cause hydrogen to be changed to helium. In the process, energy is released. In the case of our Sun, we see and feel this energy as light and heat. Most stars give off similar energy, but they are too far away for their heat to be felt on Earth, and they appear as only points of light in the sky. About 90% of all stars, including our Sun, are main sequence stars, in the most stable part of their existence. The smallest mass possible to form a main sequence star is about 8% that of our Sun, or 80 times the mass of the planet Jupiter. If a protostar's mass is below this, nuclear reactions cannot take place. When a star like our Sun runs out of hydrogen to fuel nuclear reactions, it becomes a red giant.
It begins to burn helium, which is a more volatile fuel, if you like, or a higher energy fuel. It doesn't last as long, but it bloats the Sun up. So the Sun will get like 100 times brighter or more, and it'll get maybe 10 times bigger or a few tens of times bigger. The planets, of course, will suffer during that phase. The Earth, if it still has oceans, then they'll certainly boil off at that point. That phase lasts for a few 100 million years.
The outer gas layer of a red giant eventually spreads so far that it separates from the body of the star altogether.
And then the sun blows off any remaining hydrogen and makes a beautiful nebula, what we call a planetary nebula. It doesn't have anything to do with planets, but that's what we call it.
All that remains of a smaller star, like our sun, is its core.
What's left is the core of burned helium. So helium burns into carbon and oxygen mostly. So you get this half a solar mass or so of carbon and oxygen is what's left over when the star dies. It's a very dense core. It's only about the size of the Earth, but it has half the mass of the sun. That's called a white dwarf.
Astronomers have identified about 500 of these stars. 2 of the 20 stars closest to Earth are white dwarfs. One teaspoon of matter from a white dwarf would weigh about 900 metric tons. Giant and supergiant stars with a mass at least 8 to 100 times greater than our Sun face a different fate. Betelgeuse, a red supergiant, is so large that it actually appears as a disk when viewed through the Hubble Space Telescope, even though it is 520 light years away.
It runs out of fuel in the center, and not just hydrogen or helium, it burns all the way up through the elements, all the way up to iron. And it turns out iron is not a good fuel anymore. So it's stuck at that point. It's just out of fuel altogether. And so the rest of the star comes rushing in on it, bounces off, basically, and it blows off in a gargantuan explosion, which we call a supernova explosion. Most of the mass of the star is lost that way, and you end up with something that's 1.5 times the mass of the sun, and it's either a neutron star, or if you have more mass, it may be a few solar masses in a black hole.
A neutron star has more mass than a white dwarf, but maybe less than 10 miles in diameter. It's so compact that its atoms have been crushed, leaving only neutrons.
It's basically a huge atomic nucleus, a star-sized atomic nucleus. Or if there's too much mass in the star to even allow that, then the neutron star is also crushed, and then you get a black hole.
The very largest red supergiant stars, like the Pistol Star, will become black holes. Enormous gravity wells so strong that not even light can escape. Even the most casual observer can see that stars vary in brightness and color.
The star's color just depends on its temperature. That's all there is to it. And if you think about an oven, as you heat up the oven, the elements get red. That's cool for a star. Very cool, actually. Only the brown dwarfs are really that cool, as cool as your oven elements. So those are glowing a deep red. If you made it even hotter, then it starts to be yellow, like the sun. And if you make it even hotter still, it starts getting bluish, and bluish-white is for the hottest stars.
A star that looks bright might really be a very dim star that happens to be close by. And a faint star might really be a very luminous star that is extremely far away. How do we know which is which? A star's spectrum can tell you that and more.
Astronomers are like detectives. They can't really get to the crime scene. They have to just use the clues that they have. And in the case of stars, the only clue that we have is light. Now, visible light is the one you're familiar with, what your eye sees, but in fact, light comes in all kinds of varieties. We call them different wavelengths or different frequencies of light, different energies of light, and a star puts out all of those.
For example, if you pass sunlight through a triangular prism, you'll see it break into bands of color, its spectrum. But this visible part of light is but a tiny portion of the whole picture. A huge invisible spectrum of radiation extends in both directions from the edges of the rainbow. Radiation that humans can't see but can measure with special instruments. If you could see beyond red, you would encounter the infrared. Our senses only allow us to feel infrared as heat on the skin. Infrared merges gradually into microwaves and the familiar radio portion of the spectrum. Shorter than violet, you would see the ultraviolet that gives us tans and sunburns. Then you would encounter dangerous X-rays. And finally, deadly gamma rays.
So there's much more information than your eye can tell you. And so astronomers today have the technology to use all these different wavelengths of light to learn more about the star.
To analyze a star's spectrum, astronomers channel its light through a spectrograph affixed to a telescope. The spectrograph breaks the starlight into its component colors and records its spectrum.
So I break the light up as much as we can, and then there's a lot of detailed physics that you do to understand it, but then it gives you a lot of detailed information. So I can tell you what the star is made of, I can tell you what the temperature is at various points in its atmosphere, I can tell you how the gas is moving around, how much the star is spinning, whether it's turbulent, whether magnetic fields are present, whether they're getting dissipated or not, all kinds of stuff.
The Sun is by far the largest body in our solar system, containing about 99.8% of the system's total mass. Jupiter contains most of the rest. If it weren't for the Sun's gravitational pull, the planets, their moons, the asteroids, and comets would all fly off into space, never to return. Like most stars, the Sun is powered by hydrogen fusion at its core. Pressure there is 250 billion atmospheres, or 250 billion times greater than the atmospheric pressure on Earth. The temperature is 27 million degrees Fahrenheit. The surface of the Sun is called the photosphere. The visible light that reaches the Earth originates here. The photosphere is about 250 miles deep and registers about 9,950 degrees Fahrenheit. It's a mass of hot gases and powerful magnetic fields. A region known as the chromosphere lies just above the photosphere. The chromosphere is between 1,200 to 1,900 miles thick. Temperatures here range from about 9,950 degrees Fahrenheit near the edge of the photosphere up to 17,500 degrees near the corona. The hottest part of the Sun we can see is its corona. This halo of million-degree gas stretches millions of miles out into space. The solar wind is an extension of the corona into space.
Solar wind, which is basically just protons, charged particles coming off the Sun. Why are they coming off the Sun? Because the solar corona is really hot. In essence, it's boiling away a little bit of its mass.
On Earth, these charged particles can cause power line surges and radio interference. They are also responsible for the beautiful light displays in far northern and southern latitudes called aurora.
We usually get protected, but if it's a really big blast, then it compresses our magnetic field, and some particles will come in through the poles of the Earth, and so that the aurora borealis is just that. It's just solar particles which get into our magnetic field, come down the polar field lines, and hit our atmosphere, make it glow.
Coronal mass ejections, or CMEs, occur in the corona and can spew out 1 billion tons of particles traveling millions of miles an hour.
Coronal mass ejection is a disruption in the upper corona that spews hydrogen into the solar system. The flare is an energetic explosion near the surface of the Sun, usually. There are beams of high-energy particles which travel down the magnetic field, strike the surface of the Sun, heat it up a lot, and so you see this brightening on the surface of the Sun.
It takes about 1 million years for energy released at the center of the Sun to make its way to the surface. That means that if nuclear reactions at the Sun's core ceased today, we wouldn't feel the effects on Earth for about 1 million years. Like the Earth, the Sun rotates around an imaginary line through its center called an axis, with a North Pole and a South Pole. But unlike the Earth, which rotates as a solid body, the Sun's rotation is not uniform. At the equator, the surface rotates once about every 25 days, while at the poles it can take as much as 36 days. Electric currents in the Sun caused by its rotation generate a complex magnetic field. As the Sun rotates, this magnetic field twists into a large rotating spiral that extends well beyond the orbit of Pluto. Sunspots are places where the sun's surface or photosphere gets warped by its magnetic field.
They look like dark spots on the sun, and they're not really dark. They're just darker than the rest of the sun. So they are maybe 1,000 degrees cooler than the rest of the surface of the sun. They're caused when big tubes of magnetic flux come up out of the sun. When it does that, basically it interrupts the flow of energy out of the sun in the places where it's coming out, and so those cool off a little bit. So that's why you get sunspots.
Sunspots can come in many sizes. Most are about twice the size of the Earth. The prevalence of sunspots varies in a regular cycle.
Every 11 years, the sunspots reach a peak in number, and then they die back down again. Then they come up again, but they're all turned around. The North Poles and South Poles are basically reversed. They peak again, then they go back down, and then it repeats the other way. So it's a 22-year cycle, but as far as counting sunspots, it's an 11-year cycle.
Sunspots are important to us on Earth because there appears to be a correlation between the number of sunspots and the output of the sun.
Well, we're not completely sure, but what we do know is that the overall output of the sun, and this is very paradoxical, is a little higher when the sunspots are numerous than when they're not. And now, that's not because of the spots. The spots, of course, are a little cooler, so they drop the output. But it turns out the magnetic fields around the sunspots create extra heating, and that more than compensates for the cooling of the spots themselves. So the sun gets a little brighter when sunspots are present, and a little dimmer when not. We don't truly understand the connection with the Earth's climate, but we're pretty sure there is one.
There was a period of very low sunspot activity in the latter half of the 17th century called the Maunder Minimum. It coincides with an abnormally cold period in northern Europe, sometimes known as the Little Ice Age. Life as we know it on Earth is completely dependent on energy from the sun. Plants use energy from the sun to make food. In this process, they also take in carbon dioxide and give off oxygen that animals breathe. Plants also provide food for other organisms. Oceans and seas store the sun's energy in the form of heat. This heat sink feature moderates temperature, allowing for a wide variety of life to exist on Earth. The sun is also responsible for our wind and long-term weather patterns. And solar activity can affect our communication systems and satellites.
The sun is absolutely crucial to the Earth, right? We wouldn't be here if it weren't for the sun. And of course the sun is far more powerful than anything on the Earth too. So we would like to understand what it might be up to, what its likely future behavior will be.
A number of space missions are underway to collect data on the sun.
But what we really want from spaceborne observations is to look at the wavelengths of light that don't get through the Earth's atmosphere. So for sure you want spacecraft to do gamma ray studies, X-ray studies, ultraviolet studies, and even some infrared. The other thing you get from space is really sharp images. You don't have our atmosphere blurring you.
The objective of SOHO is to investigate the sun's corona, the solar wind, and the sun's interior structure, focusing on flares and coronal disturbances. RESI studies solar flares in X-ray and gamma-ray light. It can also see gamma-ray bursts from high-energy sources throughout the universe. The WIND mission provides information on the solar wind as it enters the Earth's magnetic field and upper atmosphere. 4 cluster spacecraft complement the WIND mission. They orbit within the Earth's magnetosphere to collect data on the interaction of the solar wind and the Earth's magnetic field.
We have a number of spacecraft which fly around inside our magnetic field. They try to figure out where the particles are going when they hit us and what kind of magnetic rearrangements take place. And it's very complicated, and people have been trying to understand exactly what happens, because it's important, again, to understand what will happen to satellites and electronics and so on when the sun hits us.
Our sun is considered middle-aged. Since its formation about 4.5 billion years ago, it's used up about half the supply of hydrogen in its core. It's currently made up of 70% hydrogen and 28% helium by mass. But over time, as the sun continues to convert hydrogen to helium, its composition will change. As helium continues to accumulate, pressure at the core will increase, and the sun will grow brighter.
While stars are on the main sequence, they slowly brighten. This is as they're basically using up their hydrogen. And that slow brightening of the sun will be important to the Earth a little later on, and I'm speaking astronomically, of course. Some people think that the Earth is only going to remain habitable for another 500 million years or so, based on the fact that we understand what the sun is doing over time. Now, 500 million years is probably plenty of time for us to do something about it, but it's good to know, that we should start thinking about that.
In 3 billion years, the sun will become hot enough to boil away the Earth's oceans. In 7 billion years, it will have used up its core hydrogen supply and grow into a red giant that engulfs the orbit of Mercury. The outer solar system will grow warmer and more hospitable. The icy moons of the giant planets may become warm enough to be covered with liquid water instead of ice. Finally, about 8 billion years from now, the sun will blow off its outer layer and collapse into a white dwarf. Lucky for us, this sequence of events is so far in the future that we don't have to worry about it. In the meantime, we continue to study the sun to find out how it affects us both on Earth and in space. Perhaps you'll be the one to determine the connection between sunspots and Earth's climate, or find a better way to protect our satellites and communication systems from damaging solar radiation.
I can't imagine humanity turning its back on these questions and stopping to wonder. I think we wouldn't really be people anymore if we did that.
Space presents a limitless frontier for exploration. Are you ready to meet the challenge?